Hi, thank you for joining us again. Welcome back to the course on Introduction to Material Science and Engineering offered by EdupediaWorld. Previous several lectures we have been understanding the idea about crystal systems and we saw the different type of crystal systems that exist both in the metallic world and in the ceramic scenario. Today we will jump into one very important concept that is important in context of crystalline materials. We'll be understanding the idea of crystallographic directions and crystallographic plane. Today's lecture will be focusing on crystallographic direction, but before that, let us introduce you to the idea that why do we need to understand crystallographic directions and planes and what exactly are they. So as I said, with the background of crystal structure, now we are ready to understand the crystallographic directions and planes. But why do we need to understand it? The reason is quite simple. The reason is that the deformation or any deformation which takes place in a metal or a ceramic takes place in certain directions and in certain planes. Okay, so we need to know which are the directions and planes which are favorable for deformation, and thereby we can identify those planes and directions and follow the phenomena and understand the physics behind it. Secondly, there are several material properties like conductivity or elastic modulus for different materials which can vary with directions or which can vary with the crystal orientation, the orientation in which the crystal is existing. So in order to understand those physical phenomena, we need to have a background of the crystallographic directions and plane. Therefore, we need to understand both these concepts. To begin with, today's lecture will focus on crystallographic directions. So what is so important about crystallographic direction? As I already mentioned, we need to understand it to understand the basic physics behind different kind of deformation and stuff. There is a need to establish a convention beforehand to understand both crystallographic direction and plane. That is, everyone who studies material science or metallurgy should use a unique set of ideas to represent a particular direction. There should not be any confusion. Therefore, a convention needs to be established. The convention that is used is known as Miller indices. Okay, and this Miller indices is used to define specific direction and specific plane. How do we do that? We'll see further down the line. The idea is that any unit cell which you have seen till now, the cubic unit cell for example, can be defined by three axes: the x-axis, the y-axis and the z-axis, right? Or the z-axis. So we use those three different directions as the three edges of a coordinate system which we define, and based on that coordinate system we define the crystallographic direction. First of all, I will give you a theoretical idea about what or how we are going to do it, and then I will practically show you with figures and examples. How do we define direction in general as well as in this specific case of crystallographic direction? So for any direction, imagine you want to establish the direct direction from your home to your school. So your home is one point, your school is another point, and you draw a line from your home directly towards your school. That gives you a direction. That may be north, northeast, or 15.5 degrees south of east, something like that, right? So you have a specific direction using the convention of south, east, northwest. Similarly, here what we use is that for crystallographic direction we use the vector representation, and by vector representation what I mean, it's parallel to the example of school and home which I just gave, is that we connect 2 points in the concerned direction, and then what we do is this vector which we have got, we shift it such that one end falls, the starting point falls at the origin. Okay, now we have one end at the origin of the unit cell and the other end is pointing towards any specific direction. Now that end will kind of help us define that direction of the whole direction. So what we do is that now we vector project the vector on 3 axes, and then we measure the length imparted by the vector projection on each of the 3 axes. Stay with me, I'll show you it practically. Then they are reduced to the smallest integral ratio. The 3 indices which we got by the vector projection are then represented as H, K and L in this kind of bracket. You need to use the square bracket to represent the direction. And important point here is this square bracket is used for a single direction, but if we have a family of direction, I'll come to what a family of direction is, but if we have a family of direction, we can represent it by this curved bracket with HKL, the Bravel indices mentioned inside the curved bracket. Now what is a family of direction? A family of direction refers to all the directions which can be expressed like this. For example, a family of direction for 1, 0, 0 is the direction 1, 0, 0, 0, 1, 0 and 0, 0, 1, okay, for the cubic system. So this gives you an algorithm of the step-by-step definition of how to find the direction, crystallographic direction, but I'm quite certain this does not give you any insight about how exactly to do it. So let me try to show you roughly over here and explain what I meant by each of them, or let's do it in the next page. So here I already have a cube. We will be discussing about the cubic system for the time being, and what we do is that we first establish our coordinate system. I normally use this as my x-axis, y-axis and z-axis. Remember that the axis selection should always be such that it follows the cross rule, that is x cross y should be pointing towards the z direction. Okay, the cross product rule should not be invalid. So this is the convention I will use. Therefore this direction is the x-axis, this is y-axis and this is the z-axis. Therefore what we find out that this is the origin, right? This point is the origin of the unit cell. Now suppose you are said that you need to find the direction 1, 0, 0, 1, 0, 0. So how do you find out the direction? Is that you take one step towards the x-axis, along the x-axis. So one step along the x-axis will be from here till here, right? So we start from here and we are at present over here. Then y-axis we take 0 steps, so the arrow remains here. Z-axis we take 0 steps, so the arrow stays over here. Therefore 1, 0, 0 direction is given by this axis. So this in fact is the x-axis itself. So 1, 0, 0 direction is this direction. Similarly, if we want to find out the 0, 1, 0 direction, how do we do that? 0 in the x direction, so it remains at the origin. 1 in the y direction, it goes till here. 0 in the z direction, so it remains here. Thereby 0, 1, 0 is nothing but the y-axis. Okay, so this is 0, 1, 0. This was 1, 0, 0. By similar logic extension, 0, 0, 1 will be 0 step in x-axis direction, 0 step in y direction and 1 step in z direction. So we have the 0, 0, 1 in this direction, right? Now this was an example where we already had the Bravais lattice, Miller indices. These were the Miller indices, right? And using that Miller indices, we found out what is the direction of that Miller indices. Now let us say that the Miller indices is not given, but the direction is given and you are asked to find out the Miller indice. That is where our algorithm over here, the algorithm which I have shown here, will be used. So let me do that. Let's say we have to find the direction of Miller indices of this direction. Now let me define it for you. This length is 1 unit, okay? then this length, this much in the y direction, is half unit, and this length or this length in the z direction is also half unit. So what we have done is, to move in this direction, we have actually moved 1 unit in the x-axis direction, half unit in the y-axis direction, and half unit in the z-axis direction. Thereby we have got this line. Therefore, what will be the Miller indices for this line? This line Miller indices will be 1 in x-axis, half in y-axis, and half in z-axis. But as I had said in the algorithm, that and this is a matter of fact or a convention, this is a matter of convention, that we do not keep fractional Miller indices. We do not keep fractional Miller indices in crystallographic direction. So what we will do is 1 half needs to be converted to the nearest integer. How can we do that? We can do that by multiplying it with such a number that all the fractions gets converted into an integer. So if we multiply all the 3 indices by 2, so if we multiply it by 2, then what we get? We get 2 1 1. And now I make a claim that this direction and this direction are the same direction. Okay, fair enough, I have made a claim, but how do we verify this? How do we say that this and this direction are the same direction? Let's see. Let's try to figure out what is this direction 2 1 1. So for 2 1 1, what we need to do is we need to go 1 step, 2 step in the x-axis direction. So I have gone 2 step in the x-axis direction, 1 step in the y direction, so I go from here till here, and then 1 step in the z direction. So basically I come in the z direction 1 step. Thereby what you will get is, ultimately you will get something like this. Okay, so this will be something which will be 2 1 1. I'm certain it's a bit confusing here because this is a 3D projection which I'm trying to draw in 2 dimension, but take my word for it, or you can actually draw 2 cubes here, right? 1 cube and 1 cube of the same dimension over here too, and then you try 2 steps in x-axis, 1 step in y-axis, and 1 step in z-axis, and see that it will be the same line but extended and just twice the length of this line. Thereby my claim that this direction and this direction are same is a valid claim. Okay, so you can say, I can express this also as 4 2 2. Obviously you can do that, but as a matter of convention, what we do is we keep it to the smallest integer. Okay, so this gives you an idea about if you have Miller indices given, how to draw the direction out of it, or if you have the direction given, the arrow drawn, then how to find out the Miller indices out of it. Right, let us use some more practice. Here let's try to figure out what will be 1 1 1 direction. So for 1 1 1 direction, what we will do, again my convention will be same, x, y and z axis. So I take 1 step, this is my origin, I take 1 step in the x direction, then 1 step in the y direction, then 1 step in the z direction, I reach over here. So my initial position was here, final position is here, so the direction 1 1 1 is basically this direction. Okay, this is 1 1 1. Now let us try out 1 1 0. 1 1 0, again the same thing. It's a simple exercise. You just need to keep your convention intact and follow the number of steps provided here. So 1 step in x-axis, 1 step in y-axis, 0 step in z-axis. So it ends over here, starts from here, therefore it will be like this. This should obviously be a straight line. 1 1 0. Now let me bring an interesting example. 2 1 1. How do I draw 2 1 1? 2 1 1 means I take 2 step in the x-axis, so I go from here to here, okay, till here. Let me actually draw another cube, okay, so that you can visualize it easily. So this is roughly my second cube, which is of the same size as this cube, and now I want to go 2 step in the x-axis. So this is 1 step, this is 2 step, I have reached here. Then I go 1 step in the y-axis, so I have reached here, and 1 step in the z-axis. So ultimately I end up here, starting from here. So the 2 1 1 will be basically this direction, 2 1 1. Okay, if we go back one step, this is the same 2 1 1 which I tried to draw in this slide, right? So you can see that the 2 1 1 is actually passing through, that point I talked about. It is passing through this point. So here we have verified our claim in the previous slide. Okay, now let's draw a few more lines and try to figure out what are the crystallographic direction for those lines in the cubic system. Let's say I have this direction. What will be the Miller indices for this direction? And I am using the same convention, the x-axis, y-axis and z-axis, and I say that this is again half the length, 1 by 2. Okay, so how can I get from here to here? What I need to do is I need to traverse half length in x direction, this is half x, and one complete length in y direction, right? One complete length in y direction, and in z direction I don't need to go anywhere. So what is happening is I went half x, 1 y and 0 z. Now multiplying it by 2, I get 1 2 0. So this is 1 2 0 direction. One thing which I forgot to mention is while writing down the direction in the Miller indices format, there should not be any commas here. It is read as 1 2 0 and it is written the same. Now suppose I have something, let's do something a bit tricky. Okay, let's do the starting point here and the ending point here. Okay, so now the direction which I have is not starting at the origin, rather it is over here and it goes till here. So what I can do is either I can shift this vector parallel to itself and bring it over here, right? Or what I can do, I can redefine the axis as, or redefine the origin as the origin to be here rather than there. Okay, so let's do it by redefining the origin. This I am taking as origin now, 0 0 1 0 0 0 rather. So let me draw it out, x y and this is z. So what is happening? How do I get from origin till here? What I need to do is I need to take one step in x direction but in the negative direction of x, right? So let me first write it down, -1 in x direction, 0 unit in y direction. Okay, 0 in y and 1 in z, 1 in z, 1 in z. So this is my direction for this vector, which is -1 0 1. But in the crystallographic direction reference, we do not use -1, rather we write it as bar 1, bar 1 0 1. So this direction is bar 1 0 1. Fine, I made one mistake over here, is that I said one step in the y direction. Actually there is 0 step in the y direction and 1 step in the z direction. So it should be 1 0 2. Pardon me for that. Fine, coming back to this, what I have pointed out is that you might have negative Breville indices, Miller indices, right? So if you have negative Miller indice, what you do is you represent it by a bar instead of a minus sign before. That is the convention. Okay, let's close with one more example. Let's say if we have something like this, and this direction is 1 by 3. Now since we are starting from here again, I am putting the origin here. I am going in x direction 0 units, y direction is 1 by 3rd unit and z direction is 1 unit. So it will be 0, y direction 1 by 3 and z direction 1, and this I rewrite it as 0 1 3 by multiplying by 3 so as to get the smallest integer at each place. Now this must have given you a good grip about how to find crystallographic directions and in case of cubic systems. Let us see example of body centered and face centered. In the body centered example, if you remember correctly, we know that the body diagonal is the diagonal along which the atoms are touching each other. So let's find out that Miller indices for the body diagonal. What is the body diagonal? This is the body diagonal, right? Passing from the body, coming from this end to this end. Again, x, y, z. So what is happening? One step in x direction, one step in y direction, one step in z direction. So the body diagonal is 1, 1, 1. So our closed packed direction for a body centered cubic is 1, 1, 1. This is quite important, which we'll utilize while studying deformation. So closed pack for BCC is 1, 1, 1 direction. Why is it called closed pack? It is called closed pack because that is the direction in which the atoms are touching each other. Now for a face centered cubic, if you remember, we had the atoms touching each other along the face diagonal. So what is the face diagonal? The face diagonal would be something like this, or something like this, or something like this. So basically it should pass through the face center, right? Now if we want to find the direction of this, how do we find that? Y, x, z. One step in the x direction, one step in the z direction, 0 in the y. So this is 1, 0, 1. Similarly, this comes out to be 0 in x, 1 in y, 1 in z direction, and this comes out to be 1 in x, 1 in y, and 0 in z direction. So basically we see that the family of line of 1, 1, 0 is the closed pack direction for FCC. So this is closed pack direction for FCC. Okay, so now what you have learned till now is that you learned about how to find the crystallographic direction in case of a cubic system. In addition to that, what we learned is the closed pack direction for body centered case as well as for the face centered case. Okay, there are more closed pack directions in this too. What are the directions? If you go from this diagonal to that diagonal, or this diagonal to that diagonal, all will ultimately lie in the family of this. With this, I will close the lecture for the day. The next lecture will continue with the crystallographic direction for hexagonal systems. Till then, have a great day. Goodbye.